We are living through the biggest AI boom in history. Just look around. DeepSeek took the world by storm. ChatGPT secured $40 billion in the largest private tech deal ever recorded. Cursor AI is approaching decacorn status barely 2 years after launch. But here is what everyone is missing. Where do all of these AI platforms actually live? In the cloud. Every single one of them. Cloud infrastructure is the essential foundation making large-scale AI deployment possible. And while everyone's attention is on no-code AI automation agencies, cloud engineers stand at the intersection of two explosive trends that investors are pouring billions into. So, what is the opportunity? It's mastering how to bridge cloud infrastructure with AI systems to build the intelligent layer that creates genuine competitive advantages for businesses today. I'm Suleiman. I've worked in tech for a decade. I run my own AI cloud security consultancy, and through my academy, I've helped more than 400 students learn cloud and AI with my first principles blueprint for engineers. And in this video, I'll walk you through the 3 critical phases that will teach you exactly how to become an AI cloud engineer so you can position yourself to take advantage of this AI boom. And we're not just talking theory. At the end of each phase, we'll build real projects together, each one building upon the previous foundation, starting with phase number 1, the cloud fundamentals for AI workloads that you need to master. And there are 4 core components: compute, storage, networking, and identity management. And we're going to start with compute, which has 3 different options. And option 1 is EC2. For traditional cloud applications, you might choose a standard EC2 instance for most workloads, primarily optimizing for cost, because it gives you more control. But AI workloads are incredibly compute intensive, meaning you will need to work with specialized hardware that most cloud engineers have never used before. Now, as an AI cloud engineer, you'll provision GPU-equipped instances that can be 10 times to 20 times faster for deep learning than regular CPU-only instances. But here's the catch. They can also be 10 to 20 times more expensive, costing $30, $40, or maybe even $50 per hour. And why does that even matter? Well, when you're building cloud infrastructure for AI systems, it's not just about balancing costs, but you're actually weighing up computational power against model performance requirements. And this fundamentally changes how you approach scaling. Now, traditional cloud applications typically scale horizontally, so you just add more of the same instances when the load, i.e. the traffic, increases. But for AI workloads, you need a more balanced approach to scaling that combines both horizontal distribution, i.e. multiple nodes working together, and vertical components, i.e. more powerful GPUs per node. Frameworks like TensorFlow or PyTorch are designed specifically to distribute training across multiple GPU instances. And you also will need to be much more strategic about resource utilization, potentially using automated scheduling to ensure expensive GPU instances aren't sitting idle and costing you when they're not being used. And that's where option number 2 comes in: containers. Containers are essential for AI deployments, but in a different way than traditional applications. Using Amazon ECS or EKS, you can package your AI models with all of their dependencies into containers. And this solves a major headache since AI frameworks often have complex specific version requirements that are notoriously difficult to manage. Now, unlike traditional cloud applications where containers might have similar needs, AI workloads require containers with vastly different profiles, some needing GPUs for training, others just CPU for pre-processing. For AI workloads, containers offer 3 different key benefits. Firstly, they ensure your model works consistently across environments, from development laptops to production servers. And this eliminates that it worked on my machine problem. That's especially common with AI dependencies. Secondly, containers help you manage the varied resource needs in an AI pipeline. Your training container might need massive GPU resources, while pre-processing might only need CPU, and inference could fall somewhere in between. Thirdly, container orchestration helps you maximize expensive GPU utilization. Instead of having dedicated GPUs sitting idle between jobs, orchestration tools can automatically schedule different workloads to share these resources efficiently. Now, in practice, this means you'll use container services not just for running applications, but for creating flexible, cost-efficient AI pipelines where each component gets exactly the resources that it needs and when it needs them. Option number 3 is Lambda. AWS Lambda also plays a different role in AI architectures compared to traditional applications. Lambda's serverless nature makes it ideal for handling the event-driven aspects of AI pipelines without maintaining costly running servers. However, Lambda comes with significant limitations for AI workloads. Firstly, there is a cold start problem. When a Lambda function hasn't been used recently, it can take several seconds to initialize. For traditional applications, this might be acceptable, but for AI inference, where milliseconds matter, this latency can be problematic, especially for real-time applications. Now, additionally, Lambda has strict resource constraints, maximum memory of 10 gigabytes and execution time limits of 15 minutes. These limitations make Lambda unsuitable for processing large data sets or running complex models that require sustained compute power. Now, most AI models simply won't just fit within these boundaries. That said, Lambda still has its place in AI architectures. It's excellent for lightweight pre-processing, triggering model training jobs. But for core AI computation, you'll typically need more robust compute options like EC2 or container services. Now, before we talk about storage, the key insight here is that understanding compute options for AI workloads is more than just spinning up instances. It's about selecting the right hardware for each phase of the machine learning workflow. And this is very different from traditional applications where you might use the same instance type for your entire application. Next up, we have storage. For traditional cloud applications, you might use S3 storage to store website images, backups, or temporarily hold files during transfers. It's pretty straightforward. You create folders, organize files, and retrieve them when needed. But for AI workloads, storage becomes something much more complex. So instead of just storing files, S3 becomes the foundation of what we like to call a data lake. Essentially, a massive central repository that feeds data into your AI models. The scale is dramatically different. AI systems routinely handle terabytes or even petabytes of data. And to put that into perspective, a petabyte is 1,000,000 gigabytes, enough to store about 500 billion pages of text. And this enormous volume changes everything about how you organize your storage. So instead of simple folders, you'll use specialized data organization techniques like Apache or Delta Lake. They are frameworks that help you efficiently search through and maintain consistency in massive data sets. And as an AI cloud engineer, you will organize your data storage into different zones. A zone for raw, unprocessed data, a zone for processed features, i.e. the specific data points your AI will learn from, a zone for storing the actual AI models that you create. And this layered approach is necessary because each stage has different requirements. Raw data needs to be preserved exactly as it was collected. Features need to be quickly accessible. Models need careful version tracking so you know exactly which version is making predictions. Performance needs also change dramatically. While regular applications might be fine with standard storage options, AI training is extremely data hungry and needs much faster data access. You often use premium high-speed storage options that would be unnecessarily expensive for regular applications. And when working with multiple powerful GPU machines for AI training, you'll need special file systems like Amazon EFS configured for maximum performance to share data between them. This becomes especially important when your AI training is distributed across multiple machines that all need access to the same data sets. Perhaps the biggest shift in thinking as an AI cloud engineer is seeing storage not as static containers, but as a continuous pipeline. Now, data in AI systems follows a journey. It starts as raw information, it gets cleaned and processed, it becomes training data, and eventually feeds the models that make the predictions. Each stage in this pipeline needs different storage optimizations. Think of AI storage like setting up a factory with assembly lines that continuously process raw materials into redefined products. Number 3, networking. For traditional cloud applications, your VPC might be designed around typical web traffic patterns. External users connecting to load balancers with traffic flowing to application servers and databases. But AI workloads create very different networking demands. The biggest shift in your networking mindset will be optimizing for unique traffic patterns of machine learning lifecycle. As an AI cloud engineer, you need to understand that each stage of building your AI systems has drastically different networking requirements, and your infrastructure needs to adapt to these changing demands. We can break this down into 3 different levels, starting with level number 1, data ingestion. This is where you bring your training data into your AI environment. You're often moving enormous data sets, customer data, images, videos, or text that your AI will learn from. Standard network connections would be insufficient for these data volumes. You are transferring terabytes or even petabytes of data, requiring specialized high bandwidth network configurations. AWS services like Direct Connect are commonly used during this phase to create high throughput pathways for data movements, which will reduce transfer data times from a few days to just a few hours. VPC endpoints become critical during this phase because of the massive data volumes involved. They allow your resources to communicate with AWS services without going through the public internet, saving thousands of dollars every single month in data transfer costs whilst improving security. Level number 2 is distributed training. Once your data is in place, training begins. When training large AI models, you need to split the work across multiple powerful computers. This is very different from traditional cloud applications. In traditional applications, your server will mainly talk to your users or to your databases. But in AI training, the machines primarily talk to each other, constantly sharing what they are learning from the data. This communication happens thousands of times per second. This creates two major challenges that don't exist in traditional applications. Firstly, even tiny network delays, i.e. just milliseconds between machines, can add up to dramatically longer training times. When you're paying over $30 per hour for each GPU machine, these delays directly impact your budget. Secondly, the networking needs are completely different. You will need specialized configurations to handle the massive machine-to-machine communication. Now, to solve these problems, you will use AWS placement groups with the cluster strategy. This physically places your machines close together in AWS data centers to minimize network delays, Elastic Fabric Adapter or EFA, a specialized network card that lets computers communicate more directly by passing parts of the operating system. These networking optimizations can cut training time by 30 to 50% compared to standard networking, a huge efficiency gain when running expensive GPU instances. You will also need to configure security groups for different AI workloads. While traditional applications might only need to allow web traffic on ports 80 or 43, AI training requires opening specific ports between your training nodes. This is because AI frameworks like PyTorch Distributed use their own communication protocols and ports to exchange model updates efficiently. Now, without these special security group rules, your distributed training simply wouldn't work, as the machines couldn't share their learning with each other. Level number 3 is inference serving. After your model is trained, you deploy it to make predictions. This is called inference. At this stage, your networking needs to completely change again. Now, unlike training, where machines constantly talk to each other, inference is about handling many smaller requests coming from users or applications. This is more similar to traditional web applications, but with important differences. In traditional web applications, you might optimize for handling high traffic, but the processing for each request is usually simple. For AI inference, each request might trigger complex model calculations that require significant computing power. This creates unique challenges. Firstly, response time becomes critical. Users expect AI predictions quickly, often in milliseconds, which means your network must be highly optimized for low latency and not just high throughput. Secondly, AI models can be very large, making them difficult to deploy globally. You will need to consider strategies like model compression or distributed inference to maintain performance. And to address these challenges, you can implement the following: specialized load balancers configured for AI workloads that can route requests based on model versions or specific hardware capabilities. You can do regional deployments to position your models closer to end users, which will reduce network travel time for requests. And these networking adjustments ensure your AI systems can reliably serve predictions with consistent, low latency, even under varying load conditions. And this balanced approach to networking is essential because in AI systems, a slow prediction might as well be no prediction at all. Next, number 4 of our core infrastructure fundamentals is identity and access management. In a traditional application, your IAM permission needs are relatively stable. Once you set up your permissions, they rarely change. Developers consistently need access to their code repositories, and database applications always need the same read and write permissions to specific tables. AI systems work fundamentally different. They don't have stable permission requirements because they are constantly evolving through distinct phases. Firstly, data engineers collect and prepare the data, needing access to storage services and raw data sources. Then data scientists experiment with models, requiring permissions to powerful compute compute resources and development datasets. Next, machine learning engineers evaluate and refine these models, accessing benchmark tools and test environments. And finally, AI cloud engineers or AI/ML platform engineers will deploy to production, requiring permissions for deployment services and monitoring tools. This creates a unique challenge you don't face with traditional applications. Your permissions are constantly shifting as projects move through these different phases. The same resource might need different levels of access on a Tuesday than it had on a Monday. This solution is attribute-based access control, or ABAC, a more dynamic approach than traditional permission systems. Attribute-based access control uses tags on your resources to automatically determine who can access what. For example, when a model is tagged as development, data scientists automatically get full access. And when that tag changes to production, their access is restricted while deployment teams gain the access, all without manually updating permission policies. This approach is essential for AI workflows because they generate so many artifacts, datasets, notebooks, model versions, and endpoints that traditional permission systems become unmanageable, creating either security risk from overly broad permissions or workflow bottlenecks from overly restrictive ones. Now you might be thinking, how can I possibly manage all of these resources without going crazy? Firstly, let me be clear. You won't be managing all of these resources by clicking around in the AWS console. That works when you're just starting out, but it quickly becomes unmanageable as your AI infrastructure grows. Instead, that's where infrastructure as code comes in. Using Terraform or the CDK or CloudFormation, you describe your entire infrastructure in files, similar to how you would write regular code. You specify exactly what resources that you want, how they should be configured, and how they connect to each other. For AI workloads, IAC becomes even more critical because AI environments are often more complex with many interdependent resources. You'll frequently need to create identical environments for development, testing, and production. You may need to replicate environments across regions for global deployments. Version controlling your infrastructure becomes essential for compliance and governance. But IAC is only half of the equation. Python makes up the other half, and here is 3 reasons why. Firstly, the AWS SDK for Python lets you programmatically control every AWS service. Need to create 50 S3 buckets with similar configurations? You can write a Python script for that. Secondly, Python is the language for machine learning. When you're building AI solutions in the cloud, you'll need to process data, train models, and evaluate results, all tasks where Python excels. Libraries like TensorFlow and PyTorch are industry standards for AI development. Thirdly, Python helps you bridge the gap between infrastructure and application code. Your IAC might deploy the resources, but Python scripts often handle the operational tasks: data pre-processing, model deployment, monitoring, and automation. By using infrastructure as code with Python automation, your infrastructure becomes documented, repeatable, and programmable. You can create multiple identical environments in minutes. And if someone on your team makes a change, you can review it in version control like Git, the same way that you would review any other code change. Now, we are going to put our infrastructure knowledge into practice by building a real project, a retail inventory management system that uses AI to predict demand and recommend products to customers. For our AI capabilities, we'll use AWS Bedrock. This is a service that gives us access to pre-built AI models for a simple API, meaning we don't need to create AI models from scratch. AWS Bedrock will help us do 2 things in our system. Firstly, it will analyze our sales history to predict which products customers will want to buy in the coming days and the coming weeks. This helps store managers know what to restock. Secondly, it will suggest relevant products to customers while they shop, similar to the "you might also like" feature that you see on shopping websites. Next, we need to decide what AWS compute services will run our application. We'll use 2 different compute services because we have 2 different types of processing needs. For responding to customers browsing our store, we're going to use AWS Lambda. These are small pieces of code that run only when needed. In our case, when a customer views a product, Lambda will gather the customer's shopping history, get information about the product that they are viewing, and send this information to Bedrock for recommendations. Then show these recommendations to the customer. For our nightly inventory predictions, we're going to use Amazon EC2 instances. These are virtual servers that will run once per day to analyze our sales data and predict what we'll need to stock in the coming days. This process takes a little bit longer and needs more computing power than what Lambda can provide. So we're using this combination because Lambda works well for quick on-demand tasks like generating recommendations, while EC2 is better for longer and scheduled tasks like running our inventory forecasting algorithms. Now we need to decide where and how to store our data. data. We'll use 3 different storage services because we have different types of data with different needs. We'll use Amazon S3 as our main data repository, what engineers call a data lake. S3 will store all of our historical sales data organized in 3 different levels. Raw sales data as it comes from our systems, i.e. the bronze zone, cleaned and organized data that's ready for analysis, which is our silver zone, and prepared data specifically formatted for our forecasting models, which is our gold zone. We'll use Amazon DynamoDB as our database for current inventory information. DynamoDB is designed for quick access to data, which is important when customers are shopping and need to see what's in stock. It will store current inventory levels, product details, and forecasting results. We'll then use Amazon Elastic Cache to temporarily store our cache, i.e. our product recommendations. This way, if many people view the same product, we don't need to generate new recommendations each time, making our system faster and more efficient. We're using these 3 storage services together because each is optimized for different needs. S3 for large amounts of historical data, DynamoDB for fast access to current information, and Elastic Cache for temporary storage of frequently accessed results. Now, let's show you how all of these components work together. When a sale happens, the data enters our system through a Kinesis data firehouse and is stored in our S3 data lake. AWS Glue processes this data, organizing through the 3 different level structures, while DynamoDB is updated with our current inventory levels. This processed data then supports 2 main functions. The first one is our inventory forecasting system uses EC2 instances that run nightly, reading the processed data from S3, generating predictions about what products will sell, and storing these predictions in DynamoDB. Store managers can then see which items need restocking. Number 2, our recommendation system activates when customers browse products. When a customer views an item, a Lambda function quickly gathers relevant data and sends it to Bedrock for AI-powered analysis, and then returns personalized product recommendations. These recommendations are cached in Elastic Cache for efficiency. But is that all? Well, no, because I purposely left out one critical part that is fundamental to our whole project, and that is phase number 2, security. You see, when the average data breach costs $4.8 million, AI cloud security cannot be an afterthought. It should be built from the ground up. And I'm going to explain exactly how to secure our retail inventory system, starting with step number 1, creating role-based access controls for each stage of our workflow. For our data preparation phase, where AWS Glue processes sales data, we are creating a dedicated role with specific permissions. This role can only read sales data from our bronze zone in S3 and write organized data back to the silver and gold zones. It cannot access our forecasting models or see customer information. What makes this different from traditional cloud security is strict separation between phases. In a standard application, you might have a few roles with broad permissions. Now, in our AI system, we are creating tight boundaries around each component. This separation ensures that if someone gained access to our data processing, they couldn't also access our models or our customer data. For our forecasting phase that runs on EC2 instances, we're going to be implementing a different role. This role can access processed sales data from the gold zone, run the forecasting jobs, and write predictions to DynamoDB. It cannot access raw customer data or modified original sales records. We're also setting it to only launch instances during scheduled windows and automatically shut them down when done, since these are expensive resources. For our recommendation service and using Lambda and Bedrock, we're going to be establishing a 3rd role. This role can only read customer and product data from DynamoDB, call specific Bedrock models through the Bedrock API, and write to Elastic Cache. It cannot access our historical sales data or forecasting systems. Here, we'll need multi-factor authentication for administrators who manage these systems, because compromised credentials could lead to a subtle but harmful changes to models or data access. Step number 2 is securing our network paths. Our retail system has unique network traffic patterns that need special protection. We're placing all AI components in private subnets with no direct internet access. Our Lambda functions, EC2 forecasting instances, and Glue jobs are all run in these protected environments, isolated from external threats. Now, to allow these isolated components to access AWS services, we're going to be implementing VPC endpoints for S3, DynamoDB, Bedrock, and CloudWatch. These endpoints create direct private connections to AWS services that keep our data within the AWS network instead of going over the internet. We're configuring security groups with precise rules for each component. Our forecasting EC2 instances can only communicate on specific ports needed for their algorithms. Our Lambda function can only talk to DynamoDB and Bedrock, and these tight controls limit the potential damage if any component is compromised. We're also going to be enabling VPC flow logs logs to record all network traffic and setting up CloudWatch alarms to alert us about unusual patterns. This monitoring helps us detect potential security issues, such as unusual data access or communication between components that shouldn't be talking to each other. And step number 3, end-to-end encryption. Our retail system handles sensitive data at every stage, so we need to enable encryption throughout. We are encrypting all data in our 3 zones, bronze, silver, and gold, using AWS KMS. This ensures that all historical sales data is protected. Our DynamoDB's tables store current inventory information and customer data that also need encrypting. This protects real-time information about what products are in stock and customer purchase histories used for recommendations. We're also encrypting our Elasticache cluster, where we temporarily store our product recommendations. Even this short-term data is protected from unauthorized access. For particular sensitive information like customer purchase history, we're going to be implementing application-level encryption for specific fields in DynamoDB. This requires adding encryption logic to our Lambda functions, but provides an extra layer of protection for our most sensitive data. We're creating separate encryption keys for different types of data. One key for customer information, a different key for sales transaction data, and another key for our forecasting models and predictions. Each component of our system can only access the specific key that it needs. For example, our forecasting system can use the sales data key, but not the customer information key. And this separation prevents unauthorized access between components. Step number 4, AI security monitoring. AI systems face unique security challenges that require specialized monitoring. For our recommendation system, we're validating all inputs before sending them to Bedrock. We check that the product IDs exist and the customer information is correctly formatted. We're also monitoring for unusual patterns in our recommendation requests, such as a user making hundreds of similar requests with small variations, which could indicate an attempt to manipulate the model. For our forecasting system, we're establishing baseline patterns of normal predictions. If our system suddenly predicts dramatically different inventory needs than usual, our monitoring flags this for investigation. Such changes could indicate either a legitimate shift in customer behavior or a security issue where input data has been manipulated. We are implementing data drift detection through a combination of Amazon SageMaker Clarify for bias detection and continuous monitoring solutions. If customer purchasing behavior begins to diverge significantly from historical patterns, this could affect our forecasting accuracy. So our system detects these shifts and alerts our team to determine whether they represent natural changes or potential data integrity issues. We are maintaining complete records of our forecasting process, which datasets were used when the forecasting ran, and who approved the changes. This traceability helps us track any issues back to their source. With these security enhancements in place, here is how data flows through our system. When new sales happen in our website, the data follows this path. Sales data is immediately encrypted and sent to our S3 data lakes, bronze zone through Amazon Kinesis data firehouse. AWS glue jobs operating with restricted data preparation role in our private subnet. Read is raw data from the bronze zone. These glue jobs clean and then transform the data according to our defined rules and write the processed data to our silver zone and then the gold zone in S3. At the same time, DynamoDB is updated with the current inventory levels, with all data encrypted both in transit and at rest. All of this data processing happens in private subnets with no direct access to the internet, using VPC endpoints to communicate with AWS services securely. This prepared data then feeds 2 main processes. For inventory forecasting, every night at a scheduled time, EC2 instances start up in a private subnet, operating with the restricted forecasting role. These instances read only the processed sales data that they need from the gold zone in S3 through a secure VPC endpoint. The forecasting algorithm running in this secure environment analyzes this data to predict future inventory needs. These predictions are encrypted and stored in DynamoDB for use by store operations. The EC2 instances automatically shut down when forecasting completes to minimize both costs and exposure. Now, throughout this process, our monitoring systems are watching for unusual prediction patterns that might indicate data manipulation or system issues. For customer recommendations, when a customer views a product, their request passes through the API gateway, which authenticates them. API gateway triggers a recommendation Lambda function with the restricted recommendation role. This Lambda function retrieves only the necessary customer and product data from DynamoDB with sensitive fields using additional application level encryption. The function sends this data to Amazon Bedrock through a secure VPC endpoint, validating all inputs first process to prevent potential manipulation. Bedrock generates personalized product recommendations, which are returned through our secure channels. And these recommendations are encrypted and stored in Elasticache for quick retrieval if similar recommendations are needed. Now, while our secure AI inventory system is up and running, we face a big challenge. How do we keep our AI models continuously improving without compromising security? As customer shopping patterns change, our AI models need to adapt. We would need to manually process new training data, retrain models in development environments, evaluate model performance manually, deploy these new models to production by hand, and monitor performance without automated safeguards. This approach creates a painful trade-off. Either you update rarely and you fall behind your competitors, or you update frequently and you risk security or a lot of bugs. And to be honest, neither option is acceptable. But there is a solution. Phase number 3, we're going to implement an MLOps pipeline for our AI workload. This goes beyond traditional DevOps because the ML lifecycle is fundamentally different from traditional software development in 3 different ways. Number 1, data-centric versus code-centric. Traditional software development is primarily code-centric. The behavior of the application is explicitly defined in code. If there's a bug, you can just fix the code. Now, machine learning development is data-centric. The behavior of the model is learned from data. If there is a problem, it could be in the code, or it could be in the data, or it could be in how the model is learning from that data. Number 2, experimentation versus implementation. Traditional software development follows a relatively linear path from requirements to implementation to testing to operating. ML development is inherently experimental. You don't know in advance what features, algorithms, or hyperparameters will work. This requires infrastructure for tracking experiments, comparing results, and reproducing successful approaches. Number 3, dynamic versus static behavior. Traditional applications behave the same way until the code is changed and redeployed. Machine learning models can degrade over time as the real-world data they process drifts away from the data that they were trained on. This means continuous monitoring and retraining is essential, even if the code doesn't change. Just before we implement MLOps, let's brush up on the lifecycle, which consists of 4 stages. Firstly, the data pipeline. How fresh data flows in, gets processed, and is prepared for model training. Then we have training and validation, where we experiment with improved models and evaluate them against set metrics. Then we have deployment, how we safely roll out these new models into production. And finally, monitoring and feedback, how we keep an eye on the model performance over time and trigger further improvements when needed. The key point is that machine learning ops isn't a linear process. It's a continuous cycle where monitoring feeds back into the data and the model development, creating a closed loop of ongoing improvements. Now, let's transform our intelligent retail inventory system into a solution that continuously learns and improves from every customer interaction and inventory change. Right now, when a sale happens in our stores, the data flows through the kinesis into our S3 data lakes bronze zone. AWS Glue jobs then transform the raw data into useful information in our silver and gold zones. The challenge is that we have to manually trigger these jobs or run them on fixed schedules, creating delays between data arrival and processing. To solve this, we're going to be connecting AWS step functions and Event Bridge to our data pipeline. These services will detect when new sales data arrives and immediately trigger our Glue jobs, ensuring our models always work with the freshest information available. Data quality is equally important for accurate AI predictions. That's why we're adding Python validation scripts to examine incoming data before the processing begins. These scripts will catch potential problems like negative prices or duplicate records that could throw off our models. By filtering out problematic data early, we protect our forecasts and recommendations. We're also enhancing our AWS Glue data catalog to include version information for each data set. This seemingly small change will have a big impact. It allows us to trace exactly which data was used to train any specific model version. When questions arise about why a model makes certain predictions, we can look back at the exact data that it learned from. Step number 2 is automatic model training. Our current approach to model updates is entirely manual. We run nightly EC2 instances to generate inventory forecasts and use pre-built Bedrock models for our product recommendations, but updating these models requires manual input. This might create a reluctance to update the models frequently, even when new data suggests that we should. Therefore, AWS SageMaker will form as the backbone backbone of our new training system. It provides a structured environment to create, test, and deploy improved models. We'll keep all our training code in our GitHub repository, giving us complete history of every change to our algorithms and ensure we can always roll back to previous versions if needed. One of SageMaker's most valuable features is automatic experiment tracking. Each time that we train a model, SageMaker will record what data that we used, what settings that we tried, and how well the resulting model performed. This creates an invaluable knowledge base that helps us understand what works and what doesn't. Most importantly, we're establishing a comparative evaluation process. When we create a new model version, our system will automatically test it against our current production model, using metrics that matter to the business, like forecast accuracy and recommendation relevance. This objective comparison takes the guesswork out of the model updates. We only replace our current model when we have evidence that we have a new and better one. Now, replacing AI models in production environments carries risks. Currently, our Lambda functions call Bedrock for recommendations and our EC2 jobs update forecasts in DynamoDB, but we lack a structured process for safely updating these components. Now, a poorly performing model could impact customer experience or lead to inventory mistakes. Our solution begins with creating a model registry, essentially a catalog of all our models with clear status labels showing which models are in development, which are being tested, and which are actively serving customers. This registry also stores performance metrics for each model, making it easy to compare versions before any model reaches production. It will need to pass the quality gates. Some of these checks will be automatically tested of model accuracy and performance, while others might require human review from our data science team. This careful validation prevents problematic models from affecting our business, and the actual deployment will use a blue-green approach, where we run both of the old and the new model side by side for a small period of time. We'll gradually shift traffic from the old model to the new one, carefully monitoring performance at each step. And if any issues arise, we can quickly revert to the previous version without disrupting service. Our current monitoring focuses mainly on security and system uptime, with only basic visibility into model performance. This makes it difficult to detect model drift, a problem where AI models become less accurate over time as real-world data patterns change from what they were trained on. Model drift happens in retail especially frequently. Customer preferences evolve, new products appear, and seasonal shopping patterns shift. Without proper monitoring, our once accurate models will gradually make increasingly inaccurate predictions, leading to poor inventory decisions and irrelevant recommendations, affecting both the business and the user experience negatively. And to address this, we are going to be implementing a comprehensive model drift detection system. At its core are Grafana labs that visualize key performance metrics over time. We can see forecast accuracy, recommendation relevance, and system performance trends, making it immediately apparent when models begin to drift from optimal performance. This early warning component uses statistical techniques to detect drift before it becomes severe. Our system establishes a baseline performance patterns and then monitors for significant deviations. These alerts catch subtle signs of model drift that humans might miss. Changes in click-through rates, slowly increasing forecast errors, or shifts in purchasing patterns that don't match historical data. We're also implementing direct feedback collection mechanisms. The system will track whether customers engage with our recommendations, what they will ultimately purchase, and how we adjust our inventory forecasts. This feedback creates a ground truth dataset that helps us understand exactly where and how our models are drifting from reality. When drift is detected, our system takes action automatically. It triggers the training pipeline to create refresh models using the latest data patterns. This creates a closed feedback loop where model drift is continuously detected and corrected without requiring constant human intervention. The result is a self-healing system that maintains accuracy even as the retail environment changes around it. With these improvements in place, our retail inventory system transforms into a continuous learning engine. Sales data flows into S3 automatically, triggering validation checks and processing through our enhanced data pipeline. Each data set now carries versioning information, creating a clear picture between the source data and models. For inventory forecasting, our monitoring system constantly compares predicted inventory needs against actual sales results. And when accuracy begins to decline, SageMaker automatically launches training jobs that experiment with updated approaches. If a new model performs significantly better, it moves through our approval process and then gets carefully deployed using our blue-green method. For product recommendations, customers' interactions flow through our existing Lambda functions. But now, we need to capture feedback about which recommendations customers actually engage with. This information feeds back into our training system, helping future models better understand customer preferences. Regular testing introduces new recommendation approaches to a small percentage of traffic, allowing us to discover improvements without disrupting the overall shopping experience for our customers. Now, all of these MLOps enhancements operate within the same secure environment that we established in phase number 2. Our strict role-based access controls, encrypted data flows, and security monitoring remain in place, ensuring that our continuously learning system remains protected from threats. And what about the business impact? You have to remember the reason why we are implementing MLOps in the first place. I think sometimes it's easy to get into the technical things and forget the real purpose. Our retail inventory system now adapts automatically to seasonal patterns, learning from each holiday season to better prepare for the next one. When customer preferences suddenly shift, our feedback loops help the system quickly adjust its recommendations and forecasts. Instead of spending time on routine model updates, the team of engineers can now focus on innovation and addressing more complex business challenges. The automated nature of MLOps handles the day-to-day learning and improvement. And when you are actually building something like this, the decision makers at the company can clearly sit down, look at the performance dashboards, which will demonstrate exactly how much value the AI system provides. They can watch as forecast accuracy improves and see how better recommendations translate into increased sales. The true power of MLOps lies in compounding improvements. Each cycle of our feedback makes our models slightly better, and these small gains accumulate over time. What starts a good AI system evolves into an exceptional one, turning it into an asset that grows more valuable each month. So, what should you take away from all of this? Look, cloud engineers are in a uniquely powerful position right now because almost everything today lives in the cloud. And it's cloud engineers who have the best advantage point to introduce AI and machine learning into existing cloud platforms and systems. Every modern architecture that you see has 3 layers: infrastructure, platform, and application. Today, a new layer is emerging, the intelligence layer, which uses AI to make real-time decisions, personalize user experiences, and uncover hidden insights in massive data sets. And here is why that matters. Because businesses of all sizes, from startups to massive enterprises, are looking for ways to add intelligence to their products and their services. That means cloud engineers who can deploy, secure, and scale AI workloads are in high demand right now and in the future. And if you can show that you know how to spin up ML infrastructure, integrate AI services like AWS Bedrock, and build end-to-end MLOps pipelines, you are tapping into the most valuable, sought-after skills in tech. The best part is that you don't even have to reinvent the wheel. Everything that you've learned about infrastructure, networking, and security, and automation in the cloud means you are perfectly positioned. It's just now you are layering AI services and machine learning workflows on top of these infrastructure fundamentals. And over time, you'll start to evolve from a normal cloud engineer to an AI cloud engineer, someone who designs systems that actually learn and adapt to business needs. And if you're working at a company that already uses AI, look around for ways to embed AI into existing infrastructure and processes. Could you add real-time recommendations to your e-commerce application? Could you make better predictions about resource usage or automate part of your data analysis pipeline with SageMaker? Even small pilot projects can deliver huge value and help you gain experience building AI solutions in the cloud. Ultimately, it's all about business value. Companies don't just want data. They want insights, personalization, and forecasts that drive better decision-making and make them more money. As an AI cloud engineer, you can directly impact the bottom line by creating systems that serve customers in smarter ways. And that skill, knowing how to integrate AI seamlessly into the cloud, is exactly what sets you apart in today's job market. That said, if you really want to follow this path, you have to know all of the skills that you require to become a cloud engineer first. So click right here for my complete cloud engineer roadmap for 2025 and where I share everything that you need to learn.